You ever click Buy Now on something and just wonder what happens next? Feels like magic, right? Well, behind that click, there's this hidden world of automation, a high-speed ballet of robots dancing around these enormous warehouses. Today, we're going to pull back the curtain and see how engineers actually design these incredible systems before a single bolt is ever turned. So, let's get into it.
Okay, so our story starts on a super busy factory floor. You've got this massive assembly line, and it needs a constant, perfectly timed supply of parts. Engineers call them subassemblies. The problem? These parts are always coming in and being used up, which creates this huge logistical nightmare.
Now seriously, think about it for a second. If parts show up too fast, you've got nowhere to put them. If they're retrieved too slowly, the whole multi-billion-dollar assembly line just grinds to a halt. It is a super high-stakes puzzle. So how on earth do they solve it?
Well, they solve it with this absolutely brilliant piece of technology, the Automated Storage and Retrieval System, or as everyone in the biz calls it, an ASRS. This thing is the robotic workhorse at the very heart of the modern warehouse.
And you know what's so cool? The basic concept is actually pretty simple. You've got these towering racks, right? They're filled with bins. Down the middle, there's a single aisle. And in that aisle, one robot, the SR machine, just zips back and forth. It grabs new parts from what's called the pick point and then delivers the parts they need over to the drop point. Simple and effective.
So, when you boil it all down, an ASARS is a system built to do one thing just about perfectly: move and track stuff. It's all about bringing machine-level precision and incredible speed to the, let's be honest, chaotic job of managing inventory.
And yeah, you can totally see why companies pour millions into these systems. By building up instead of out, they save a ton of precious floor space. They get lightning-fast transport, they know exactly where every single part is in real time, and they just slash costs all over the place.
All right, so for the factory we're looking at, getting an ASRS was a total no-brainer. But the engineers immediately ran into a huge decision. They had two competing designs for the storage racks, and they had to pick just one.
So the two options were pretty different. On the left, you've got configuration A. It's taller and narrower, 10 bins high, 18 bins long, giving you 180 spots in total. Then on the right, configuration B. This one's shorter but wider, 9 bins high but 25 bins long. So it has more spots, 225, but it's going to take up more of that valuable floor space.
And that right there is the million-dollar question. Is more storage just always better? Or does the shape and how far the robot has to travel matter more? I mean, building both of them just to see which one works better would be ridiculously expensive and take forever. There had to be a smarter way to do this.
And of course there is. The answer is simulation. Instead of building the warehouse in the real world, you build a perfect virtual copy of it inside a computer. It's what people are now calling a digital twin. Just think of it like a super realistic video game of the factory. In this digital world, you can tweak every little variable. You can run an entire day's work in just a few minutes, and you can collect perfect data on everything, all without spending a single dime on actual steel or concrete.
The whole process is really methodical. First, you digitally build both rack designs. Then, you program the robot's physics, like its exact horizontal speed, its vertical speed, and all the rules it has to follow. After that, you just hit play and run thousands of simulated workdays. And finally, you gather up all that data and see which design actually comes out on top.
So after running 20 separate 8-hour simulations for each design, the engineers had their data. It was time. Time to see which configuration really performed better when the pressure was on. And the number one thing they were looking for was delays. You know, one of the biggest bottlenecks you can have is a part showing up at the pick point with nowhere to go because all the bins are full. So the engineers looked at the average time a part had to just sit there and wait for an empty bin.
And the results for the bigger rack, that was configuration B, they were, well, perfect. With 225 bins, it just never ran out of room. The average wait time for an empty storage spot was 0, a big fat 0, not a single delay.
Now, for the smaller rack, configuration A, there was a tiny wait. On average, a part that arrived had to wait just 2.5 seconds for a bin to free up. Now that's a delay for sure, but it's an incredibly small one.
So, case closed, right? I mean, 0 is obviously better than 2.5. You'd think the engineers would just immediately pick the larger rack and call it a day. But that's when they started to look at the bigger picture.
And this right here is why simulation is such a game changer.
It doesn't just spit out performance numbers. It lets you weigh those numbers against real-world costs. That smaller rack, it was cheaper to build and took up less factory floor space. The only advantage the bigger rack had was getting rid of a tiny 2.5-second delay.
So now, the decision looked a whole lot clearer. It wasn't just about which system was the absolute fastest, but which system gave them the most bang for their buck.
And so, kind of against what you'd first expect, the engineers chose the smaller, taller 10 by 18 rack. Yep, the one that, on paper, actually had a small delay built into its performance.
This quote from the actual study just sums it all up perfectly. The performance gain they got from the bigger rack was so tiny, so insignificant over a whole 8-hour workday, that it just couldn't justify the higher cost and the larger footprint.
And that's the key takeaway, isn't it? In engineering and in business, best is always a balancing act. The truly optimal solution is almost never the one that maxes out every single metric. It's the one that does a great job without wasting money or space. You know, this whole story is about way more than just warehouse racks. It's about the power of these digital twins to let us test and optimize incredibly complex systems. Everything from city traffic grids to global supply chains. It really makes you wonder, what seemingly impossible problem are we going to solve next by building it in the virtual world first?